Hello everyone, let's take a look at our next problem. A fair die is rolled 4 times. The probability that each of the final 3 rolls is at least as large as the roll preceding it may be expressed in the form m over n, where m and n are relatively prime integers. Find m plus n. Okay, a fair die is rolled 4 times. So basically, interesting. You know, if we roll, so let's understand the problem that we're asked here first, right? We roll the die 4 times. So we're basically, it's a fair die. Numbers are going to be 1 to 6, right? The event that we're looking for is that this number is greater than this number, and this number is greater than this number, and this number is greater than this number. So how do we want to set this up? I'm thinking if we look at all possible, do we need greater than or equal to? At least as large, so greater than or equal to. That might actually be a problem. Strict inequality might be easier. So what I'm thinking is writing down all the possible permutations or total number of outcomes here, right? Which is going to be 6 times 6 times 6 times 6. Okay. Now, if I think of any one particular combination here, you know, I'm just going to draw numbers randomly from my head here. So let's say the sequence is 2, 6. No, let's write a sequence which is successful in the sense that the last 3 are ordered properly. Let's say like 2, 4, 5, 6. Okay. So what I was thinking is that if I'm given something like this, if I interchange any two of the rolls, then it becomes a failure, right? So for any sequence of 4 numbers we put here, if they're all different, there's only one ordering which could possibly be successful. But if some of the numbers are repeated, then then we're not really interchanging these two numbers, right? Another way of thinking about this is, of all 4-digit numbers that I can make with the digits 1 to 6, or maybe not numbers, of all 4-digit strings we can make with the digits 1 to 6, how many of them are increasing? Not strictly increasing. Is that a fruitful path to go down, right? So I could do something like assume the first roll is a 1. Then the next roll, it doesn't matter what the next one is, it's guaranteed to be successful. So then we're just asking how many 3-digit strings are non-decreasing. And the things that are coming to my mind here are not really probabilistic approaches, they're more combinatorial. Which, I don't know, for some reason my instinct, that seems like a more reasonable way of doing this. So if it wasn't a 6-sided die, you know, if we were instead generating 4 random variables independently from a continuous distribution, then the answer would be 1 in 24. Right? Because given the 4 numbers, there's only going to be one ordering of them, which is increasing. And there are 4 factorial ways of ordering them in total. So I expect the answer to be approximately 124. The thing that's throwing this off is that if with a die, 2 of the rolls could be the same, in which case it's no longer one arrangement that is increasing. So maybe we break it up into cases where we have, where we break it up into cases of how many repeated numbers there are. That seems very messy. Okay, how about we simplify the problem? Roll the die twice. So this means there are 36 possible outcomes. Okay, there are 6 outcomes where we get pairs, and we know, and those are successful. And of the remaining 30, half of them will be successful because they'll be ordered in the right way. Lowest first, highest second. And so this gives 21 possible combinations out of 36, which is what? Divide by 3, 7 out of 12. That's for two rolls. What about 3 rolls? So now we have 216 possible orderings. There are 6 triplets. And then how many ways are there? And the triplets are successful. And what about the pairs? Okay, so the way we're going to figure out the number of pairs, there are 6 ways to roll 2 dice the same way. There are 6 results for the there are 5 results, 5 possible results for the non-matching die. And there are 3 ways to arrange these things, because the non-matching die can be first, second, or third. So this is 30 times 3, 90 sequences with a pair. But how many of these are successful? Well, the pair has to be together. The pair has to be either the first 2 or the last 2. So we can immediately rule out a third of these. Okay, so all the ones where the odd one out happens in the middle could not possibly be successful, because either we fail in going from the first to second, or we fail in going from the second to the third. And then of the remaining possible combinations, half of them will work. Because basically, if these 2 are the same, if these 2 are the pair and that one's the third one out, only one of these two, if I interchange the orders, could possibly be a success. Okay, so there are 30 successes when there is a pair. So how many ways are there of rolling 3 distinct numbers? Okay, so the first die, there's 6 outcomes, 5 outcomes, 4 outcomes, and 3 factorial arrangements. So what is this equal to? 30 times 4, 120 times 6. This is equal to 720. There's only 216. Oh no, the 6 times 5 times 4 is it. We don't have to multiply by 3 factorial. Six times 5 times 4, I said, was 120, right? And let's just check quickly. 120 plus 90 is 210, plus 6 is 216. Okay. So with 3 distinct, how many ways are there of ordering 3 distinct numbers increasing? There's 1. 1 out of 3 factorial will be successful. Okay, so the 120, we have to divide this by 6 to get 20. So there are 20 successes when they're distinct. So the total number of successes here (56 successes out of 216 possibilities. Okay, so the probability is 56 over 216, which is, well, I don't know, 23 divided by 108. Okay. What was the answer before? 7 out of 12, down to 23 out of 108. So is this the approach I want to take for 4 numbers? I think so. I think we can take this one step further, whatever. We can go one more step to a 4th die and just still keep track of all the possible cases of how many repeated numbers we have, how many repeated rolls, and just do the combinations. Okay, so what is 216 times 6? 1296. Okay, so this is the total number of arrangements we have. I'm just drawing these blank spaces so that I can visualize things in my head. So let's go 4 of a kind. There are 6 ways of doing this. And those are all successful. They're all increasing sequences, not strictly increasing, but increasing. Okay. So then let's say we have 3 of a kind. The 3 that match can happen in 6 ways. The odd one out can happen in 5 ways. Now, I don't really need to know how many possible combinations there are here, because after I compute how many possible combinations with 3 of a kind there are, I'm going to eliminate all the ones that are not successful. But I'm going to continue with this anyways. So 3 of a kind can happen 6 times 5 ways, and the odd one out could occur in 4 different positions, right? So this could be the odd one out, and then I have the other 3 are equal. And there's 4 places that the odd one out could end up in. So what is this? This is 120. But the only ones that are going to be successful are where the odd one out is first or last. And in fact, only half of those. Okay, so we have to divide this by 4. Okay, so the odd one out has to be successful in the arrangement. The odd one out has to be first or last. And then if it is first, then the corresponding arrangement where it is last, only one of those 2 can be successful. So there are only 30 successful arrangements where there are 3 of a kind. Okay, so let's go with a single pair. This is probably going to be the most complicated one. In fact, let's save that for later. Let's go with 2 pairs. So the first pair can have 6 possibilities. The second pair can have 5 possibilities. And how many arrangements of this thing are there? 6. You know, if I have 2 1s and 2 2s, it's basically it's 4 choose 2, right? Because if I have 2 1s and 2 2s, I just have to decide where the 1s go, then the 2s get fixed in place. I have 4 spots and 2 1s to put in them. 4 choose 2 possible ways of doing that. 4 choose 2 is 6. Okay, so what is this equal to? This is 180. Now, how many of these are going to be successful? It's only going to be successful if the pairs, you know, if that is a pair and that is a pair, and only half of those will be successful. So in fact, I have to divide this by 6, right? Takes us back down to 30 again. Let me just think about that for a second. There will be only one combination of the 6 that will work. Okay, 1 pair. How many ways how many ways are there of doing this? So there are 6 choices for the actual pair, or 6 possible numerical outcomes for the pair. Oops. The next die, 5 possibilities, and the next die, 4 possibilities. Can I skip the figuring out the total number of arrangements here? I mean, there's going to be 12 arrangements because, again, choose where the pair goes. So how many places can you choose where the pair goes? It's again going to be 4 choose 2. And then the remaining numbers go in the 2 empty spots, but there's 2 ways of doing that. So 4 choose 2 is 6, multiply by 2, we get 12. But how many of these arrangements could possibly be successful? Is it again only 1 out of the 12? Has to be, right? Yeah, the numbers are different. So the pair has to be together, and they either have to occupy spaces 1, 2, 2, 3, or 3, 4. So whatever this number is, I'm going to divide it by 12. So let's get rid of this factor of 12. This gives me 120. And now I have 4 distinct. So this is 6 times 5 times 4 times 3, which is 120 times 3, which is 360. I'm not going to bother figuring out how many arrangements there are. There are 4 factorial arrangements, but only one out of those 4 factorial arrangements will be successful because they are distinct numbers, so they have to be, there's only one order they can be in. And so this is, this is the total number of combinations of numbers, but then ordering, we'd have to multiply by 4 factorial, but then we'd have to divide by 4 factorial. So that's just going to be 360. Okay, so let's add these up. So I'll say T is the total number of successes, which is 360 plus 120 plus 30 plus 30 plus 6. Okay, and the total number of possible outcomes is 1296. So the probability is 546 over 1296. So 216 is 2 cubed times 3 cubed, and 91 is not divisible by 2 or 3. So this is lowest terms here. So at the end of the day, m plus n is 91 plus 216, which is 307. Yeah, this was, I'm fairly confident in this. I would want to go back, if I had a lot of time to work on this, I would want to go back and make sure that I didn't leave out any possible combinations of, 3 of a kind, pair, 2 pair, and so on. This is not even close to my approximate answer of 1 over 24, right? This is greater than 1/3. It's almost a half. That seems unlikely, right? What was it for 3 dice? Okay, I think I have a mistake. I must have a mistake. For 3 dice, I computed the probability is 23 out of 108, which is, about a fifth. And there's no way that an extra die makes it more likely. Unless I did something wrong in the 3 dice case. Oh, for one thing, okay, this is 28 out of 108. 14 out of 54. 7 out of 27. 7 out of 27 is about 1 in 4. $91 out of 216 is quite a bit bigger than 1 in 4. Okay, I think I have a mistake here for one thing. Okay, so 3 of a kind. The triplet can have 6 outcomes. The odd one out can have 5. Then there are 4 places I can put the odd one out. Oh no, yeah, but only one of those will be successful. So 120 divided by 4 is 30. Okay, and with 2 pairs, pair 1, pair 2. 6 ways of arranging, but only one will be successful. Okay, I'm going to do another sanity check here. So 6 ways of 4 of a kind, 120 ways of 3 of a kind, 180 of 2 pair, 120 times 12 of 1 pair. Is that where a mistake is? Because that's already way bigger than this. I honestly, I don't know what I'm doing wrong here. This is I'm clearly counting these combinations wrong somehow. This one especially. Maybe I think this should be multiplied by 6, not 12. So if I do it in the ordering, let me, I'm given there are 6 possibilities for what the pair is. Then there are 6 ways of arranging those in the 4 slots. And then the last 2 slots is just 5 times 4. Okay, let's replace this with a 6. But again, it's still only one of these combinations which can be successful. Okay, but let me add these things up again, make sure I'm counting right. Okay, so the total number of combinations I ended up getting, 360 plus 720. Plus 180, 120, and 6. $1080 plus 300 plus 6. Oh, is this still... $1386 versus $1296. Oh my God. Okay, I mean, I'm doing all the combinatorial stuff incorrectly here, clearly. I mean, this is a case where I'd want to wipe everything and just start all over again. That's what I'm going to do. I'm going to go through this kind of quickly. No, let's not clear everything. Let's just go down here. I'm going to go through this quickly. And I'm not even going to count. I'm not even going to bother with this increasing sequence business. I'm just going to try and write all the combinations, or all the numbers of combinations broken up by how many repeated numbers there are. And if I don't come out with 1296, then I don't know what I'm doing. So this seems to be where I've screwed it up, the two pair thing. And I think, I guess I was double counting. The number of possible arrangements. Anyway, what I'm going to do here is now quickly take these total combinations. These now do add up to 1296, and figure out what percentage of those are successful. So the 4 of a kind will always be successful. 3 of a kind, only one of these 4 should work. So this should go down to 30. And the 2 pair, only one of these will be successful. Okay, I'm not massively confident in this anymore. So we have 499. Not super confident here after all these mistakes that I've made. I don't know, again, I don't know if this is the best way of solving this. I didn't really use probability at all, other than knowing that every possible outcome of 4 digits has the same probability. I just asked myself how many possible combinations of these things are increasing. Yeah, I'm gonna say for now that this is my final answer, but not super confident. If I have a mistake and I figure out where it is, or if I have more comments, I'll write them in the description. Otherwise, thanks for watching.